Jai Hind students, I hope you all are keeping well and staying very fit. So continuing with the previous topics, today we will discuss these terms: conductance, conductivity. Then we will discuss certain electric symbols which will be used in electric circuits, and then we will also discuss circuit diagram for the experimental verification of Ohm's law. And last but not the least, we will discuss also about ohmic and non-ohmic conductors. So students, let's start with conductance, right? So as you are aware, conductance, it's the antonym of resistance. Resistance, we have discussed that particular topic both qualitatively as well as quantitatively. Resistance actually is the hindrance, the opposition or the obstruction offered by the positive ions of the conductor towards the motion of the free electrons. That is known as resistance. And mathematically, resistance is defined as the reciprocal of the potential difference applied across the ends of the conductor to the current flowing through it. So this is the mathematical formula for the resistance. Now, conductance being antonym of resistance, mathematically it should be given by the reciprocal of resistance. So conductance, if I represent it by G, let us represent conductance by capital letter G. It is given by the reciprocal of resistance. So conductance of a given material of a substance is defined as the reciprocal of the resistance, right? So it will be equal to I by V. Also, we are aware R is equal to rho L by A. So by using this formula, G is equal to reciprocal of resistance, it will give us A divided by rho L. So this is the mathematical formula for the conductance. Now students, regarding its SI unit. SI unit of resistance is, we are aware, it's ohm. So reciprocal of conductance would be ohm inverse. It would be ohm inverse. Ohm inverse may also be known as mho, M-H-O. So the SI unit of conductance is ohm inverse, or write the alphabets in the reverse order, or it is also known as MHO, which is mho, right? So that's conductance. Now look, good conductors will have large value of conductance, but poor conductors, which are insulators, will have small value of conductance. Right, students? Now let's discuss conductivity. Now make use of your common sense. Conductance is the reciprocal of resistance. Therefore, naturally, conductivity will be the reciprocal of resistivity. So we have already discussed about resistivity, right? Resistivity gives the measure of the resistance offered by the conductor, and remember, it only depends upon the nature of material of the conductor and upon temperature. Resistivity do not depend upon the dimensions of the conductor. Similarly, conductivity is also dependent only on the nature of the material of the substance under consideration, and obviously physical conditions like temperature. It do not depend on the physical dimensions of the conductor. It is independent of cross-section area or the length of the conductor. So students, conductivity, it is defined as reciprocal of resistivity, and let us denote it by sigma. So it is defined as reciprocal of resistivity. Now from here, resistivity is RA by L. So conductivity would be given by reciprocal of rho, so L by RA. Just now we have discussed reciprocal of resistance is conductance. So it will be G L by A. G is the conductance over here. Sigma is the conductivity, right? So the substances like conductors which conducts electricity like copper, silver, aluminium, they are very good conductors of electricity. They possess large value of conductivity. While insulators which do not conduct electricity, they possess extremely small value of conductivity. So it is simply the reciprocal of resistivity, right? For example, resistivity of insulators, it's of the order of 10 raised to 16 to 10 raised to 18. So the conductivity of insulators would be reciprocal of that. It would be from 10 raised to minus 18 to 10 raised to minus 16. Right, students? So regarding its SI unit, you are aware the SI unit of resistivity is ohm meter. So reciprocal of resistivity, that would be ohm meter inverse. Right? This is the SI unit of conductivity. So SI unit of conductivity is ohm inverse meter inverse, or as I stated earlier, ohm inverse is also known as mho. So it may be written as mho meter inverse. Mho, students, actually ohm inverse is also known as Simon. So it can also be written as Simon meter inverse. It may also be written as Simon meter inverse. So these are the units of conductivity, right? Now students, let's discuss the electric symbols. Some very basic electric signals, because in the subsequent session we will be making use of circuit diagrams. There will be measuring devices which we will be making use of, like ammeter, voltmeter. We will be making use of rheostat, resistances, right? So every conductor will offer some sort of resistance towards the flow of electric current. So the symbol of that resistance we'll discuss. So let's discuss some electric symbols now. Electric symbols. First and foremost, let's start with source. That is, I am talking about a source which will provide the electric pressure. It is only due to electric pressure, which is known as potential difference, the charge inside a conductor would tend to drift in a particular direction. It is only then it will constitute electric current. So what is the source? The cell, right? So a cell is represented like this, a single cell, it's represented like this. And as I have told you earlier, it consists of two electrodes, one is anode and the other one is cathode. One acts as the positive terminal, the other acts as the negative terminal. And chemical energy is stored, and later on it is converted into electrical energy. And it is used to provide a constant potential difference across the ends of the conductor, right? So this is the symbol of a cell. The longer line will represent the higher potential, the shorter parallel line will represent the lower potential. Second, battery. Students, the combination of cell is known as a battery. When the cells are arranged in a particular manner, in series, end-to-end connection, then it constitutes a battery. Suppose the potential difference of one cell is 1.5 volt. Then if 10 cells are connected in series, then it will become 15 volt. It will act as a source of PD of potential difference of 15 volt. So that's a battery. So symbolically, it is represented like this. So cell means a single source, battery means a combination of cells. This is a battery. This is a battery. This is a combination of cells. In this case, I have connected 4 cells. They together will constitute a battery, right? Third, resistance. As I have told you, every substance will offer some sort of resistance towards the flow of current, because when the electrons drift in a particular direction under the influence of electric field, then they very often collide against each other and also with the vibrating ions of the conductor. So their motion definitely will get hindered, it will get opposed, it will definitely get obstructed. So that obstruction is what we call as resistance, right? So every conductor will offer some resistance. And any electrical device, it is connected with the help of connecting wires to the external source. So those wires will offer some resistance. So resistance is symbolically represented like this. It's a symbol of a resistor having a fixed value of resistance. Fixed value. It is a resistor having fixed value of resistance, right? And what about a variable resistor? Variable means whose value can be changed. So it is symbolically represented like this. Just this arrow. This arrow indicates that the resistance of this particular resistor may be changed, right? There's another simple device which is used to vary the value of the resistance in a circuit, that is known as a rheostat. It is known as a rheostat. This instrument is also frequently used. Its symbol is like this. It also acts as a variable resistor. It also acts as a variable resistor. It is used to vary the value of resistance in a given electric circuit. Then, open key means when there is no continuity in the circuit, so the current will not flow through the circuit. That is when the key is open, like this. This is a symbol for an open key. Closed key. Closed key means when the key is closed, the circuit gets completed, so the current now starts flowing through the circuit. And as you are aware, the closed continuous path of the electric current is known as electric circuit, right? So this is the symbol for closed key. Then an ammeter. Now students, look. Ampere is the SI unit of current. Meter means a device which measures something. So ammeter is an electric device which is used to measure current flowing through an electric circuit, and it is always connected in series. We will discuss that in the later section. So this is the symbol of an ammeter. This is the symbol of an ammeter. Write A. In case it is written as MA, small letter MA, so it stands for milliammeter. In case it is written like this, microampere, so it will be microammeter, right? And this line, this straight line, indicates that this is a DC ammeter. This is a ammeter which is used to measure direct current. Direct current we have discussed, students. It's the current whose magnitude remains constant and it is unidirectional. So this symbol, straight parallel line, straight line, it represents a DC ammeter. While if it is like this, a wave is drawn at the bottom like this, it represents sinusoidal nature of the current. So it is the AC ammeter. It is an AC ammeter. So it is an ammeter which is used to measure alternating current. Alternating current we have discussed. It's the current whose magnitude changes continuously with time and it tends to reverse its direction periodically. So this is the symbol for DC ammeter. This is the symbol for an AC ammeter, right? And remember, ammeter is always connected in series. It's a very, very low resistance device. We'll discuss it in detail. Then, voltmeter. Students, volt is the SI unit of potential difference. Meter means measurement of some physical quantity. So this is a device which is used to measure the potential difference, right? So just as was in the case of ammeter, there can be two types of voltmeters. This is a DC voltmeter. DC voltmeter means it can measure the DC voltage, while alternating voltmeter, there is a voltmeter which can be used to measure alternating voltage, right? Its symbol is like this, sinusoidal. So it is that voltage which varies continuously with time and reverses direction periodically. So that voltage can be measured only by using AC voltmeter, and this is where the voltage remains constant, is known as the DC voltmeter, right? There are some other instruments as well, like galvanometer. It is an instrument which is used to detect the presence of current, detect the current through a circuit. If the current flows through the circuit, it will certainly give some sort of deflection, either towards right or towards left, right? And on changing the direction of the current, the needle will give deflection in the opposite direction. That's galvanometer. Anyways, these are the electric symbols which we'll be frequently using. So, we have completed the topic of conductance, conductivity and these electric symbols. Now we will discuss an electric circuit which can be used in physics laboratory so as to verify Ohm's law. In order to experimentally verify Ohm's law, we simply need to verify the fact that current flowing through a conductor is directly proportional to the potential difference applied across its ends, physical conditions remaining same, right? So as we go on increasing the potential difference, the current through the conductor should also increase proportionately. So when we plot a graph in V and I, it will be a straight line inclined towards the horizontal axis, indicating the linear dependency between V and I. So that will be the experimental verification of Ohm's law. But in order to experimentally verify Ohm's law, you need to know the circuit diagram, right? And as we have discussed, ammeter is to be connected to measure the current so that you can note the reading of the current flowing through the circuit at any given instant time. And then voltmeter, it measures the potential difference across the ends of a conductor. It is always, students, connected in parallel, right? So, electric symbol, or rather we have completed this. Now we will discuss circuit diagram for experimental verification of Ohm's law. So this is the circuit diagram. It is for the experimental verification of Ohm's law. Now Ohm's law is, mathematical statement is V is equal to IR, isn't it? R is constant. So we need to measure these two quantities. So we need to draw a circuit in which current is to be measured, for that ammeter is to be connected in series. We need to measure voltage, for that voltmeter is to be connected in parallel. And there should be a given wire whose resistance can be also found by using this particular formula. So we need to show that these two are linearly dependent. We need to show this. Right? So let's first discuss the circuit diagram for the experimental verification of Ohm's law. This is a battery. Battery, I have told you, it's a combination of cell. This end is a higher potential and this is a lower potential. A key can be connected either on left hand side or right hand side, it's up to you. So it should be closed one. Then an ammeter is connected in series. So it is the DC ammeter because this is a DC source. And then this is the conductor or the wire across which the potential difference is to be measured. Suppose this wire, standard resistance wire, it's of resistance R and a voltmeter is to be connected. So for that, what to do is, a voltmeter is connected in parallel over here, like this. This is a voltmeter, right? This is a voltmeter. So it is always connected in parallel with respect to the conductor. So it's like this. This is negative, this is positive. So ammeter is always connected in series, while voltmeter is always connected in parallel, right? So this is a very, very simple circuit diagram, and you can close this key. So the current will start flowing through the circuit. And always remember, ammeter is a very, very low resistance device. That's why it is connected in series. So it won't alter the resistance in the main circuit, so it will give the accurate value of the current flowing through the circuit. Voltmeter is a large resistance device, so that is the reason why it is connected in parallel. So it draws negligible current, and accordingly the current flowing through this resistor will more or less remain same. So it gives the true value of the potential drop across this resistor. So anyway, there is a simple circuit for the measurement of this resistance and to experimentally verify that V is directly proportional to I. Now look, in order to change the value, for different values of voltage, the current will have different values. With the gradual increase in the voltage, the current will also gradually increase, or vice versa, right? So we need to change the resistance of the circuit, the entire circuit. For that, we can make use of a rheostat. It can be connected in this particular manner. This is a rheostat. This is, I've just now discussed, this is a rheostat. So what to do is, on changing the value of the resistance, V and I will also automatically get changed, right? So this is the circuit diagram for the experimental verification of Ohm's law. This is rheostat. We need to have different values of I corresponding to different values of V or vice versa. So that is why the rheostat is required, so as to change the value of resistance in the circuit. If the entire resistance of the circuit is changed, so the current will change. If current changes, then the potential drop across the resistor will also change. So for different values of current flowing through the circuit, we will have different values of potential difference across the resistor, right? So this is the circuit diagram so as to experimentally verify Ohm's law. Now during experiment, what you need to do is that you need to take several observations, like this is V in volts, this is I in ampere, and R, it would be equal to V by I. It is in ohm. So you can prepare these columns. Now you need to take certain observations. Like in the first case, when the rheostat is offering some finite value of resistance, suppose its value is V1, the corresponding value of the current can be noted from the ammeter, and R1 can be easily evaluated from this. Right? Similarly, in the second case, the value of the resistance is changed by using the rheostat. The resistance is varied, the resistance of the circuit, not this one. So the resistance of the circuit is changed. So V2 will change, correspondingly I2 will change. But if you calculate the value of R2, which is V2 by I2, it will remain same. So R1, R2, R3, they all will remain same. More or less they will remain constant. So that verifies that the ratio of V by I is constant, or V is directly proportional to I. And if you plot a graph between V and I, you should get a straight line inclined towards the horizontal axis. This straight line, students, indicates that these two are linearly dependent. Means current flowing through a conductor is directly proportional to the potential difference applied across the ends of the conductor, which verifies Ohm's law. So after taking various readings, 4 or 5 readings, you need to plot graph between V and I. Then you should get a graph of this nature. And experimentally, you can check the ratio of V by I, which will give us resistance, will be constant. In all the observations, the value of R will be more or less same. So that will ultimately and eventually verify Ohm's law, right? Okay, so this is also over. Rest in the practicals, you can easily do it by using this circuit. Now, the last topic for this session left is ohmic and non-ohmic conductors. Students, again, just make use of your common sense. Ohmic conductors means these are those conductors in which Ohm's law is strictly obeyed. While non-ohmic conductors, these are those conductors in which Ohm's law is not strictly obeyed. Non-ohmic, so Ohm's law is not valid over there. It's not strictly obeyed, right? So what to do is, let's prepare 2 columns. This is ohmic conductors and this one is for non-ohmic conductors. Now first and foremost, what I've stated is, these are the conductors in which Ohm's law is strictly applicable, strictly valid or applicable. And here Ohm's law is not valid. This is the first and the foremost point, right? Ohmic conductors like aluminum, copper, silver, iron, these all are the good conductors of electricity, and these are the ohmic conductors in which Ohm's law is strictly obeyed, right? Provided physical conditions remaining same. Non-ohmic conductors like thyristors, like diodes, transistors, these are some semiconductor devices, diodes and transistors, there Ohm's law is not applicable, it's not valid. Second, if you plot VI graph, since current is directly proportional to potential difference or the ratio is constant, therefore we should get a straight line inclined towards the horizontal axis. It's a straight line. While in this case for non-ohmic conductors, if you plot graph within V and I, it won't be a straight line. It will contain a knee. Knee means the graph will contain a bend. It can be like this. It can be like this. So it contains a mean. So as a whole, Ohm's law is not strictly okay. So the ratio V by I is not constant. Over here, the ratio V by I is constant. Right, students? Third, in this case, resistance is constant. It do not depend on the applied voltage. The resistance do not depend on the applied voltage. So resistance is constant. That is why the ratio V by I remains constant, or V is proportional to I. That is, V is equal to IR and R is constant, which is known as the resistance. It is the constant of proportionality. So it is only possible only when the graph between V and I is a straight line. So in the case of ohmic conductors, the resistance offered by ohmic conductor remains constant as it do not depend upon the applied voltage. And such a resistance, student, is known as static resistance. Static means which do not change. Static resistance, which remains in its state of rest. That is, in this case, its value remains constant. So static resistance is that resistance which is offered by ohmic conductors and which do not depend on the applied voltage. Right? While on the other hand, non-ohmic conductors. Here, look, V by I graph, or the slope of this graph, is not constant. Therefore, resistance is not constant. So here, R is not constant. So, the resistance of diode, the resistance of thyristors, the resistance of transistors, which are non-ohmic conductors, is not constant, as it depends on the applied voltage. It depends on the applied voltage. And since its value changes, therefore it is also known as dynamic resistance. It's the opposite of static. So it is known as dynamic resistance. Right? And as I have given some examples of non-ohmic conductors are thyristors, then diodes, then transistors. These are the semiconductor devices which are non-ohmic conductors. And examples of ohmic conductors are copper, aluminium, silver. These are the normal conductors which we make use of in wiring, and they are the ohmic conductors. So students, I hope all these topics must be clear to you. So we'll continue in the next session. Till then, do take very good care of yourself. Right? Thank you.